R. Asokamani, Director for Research and Development, Dhanalakshmi Engineering College, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
In this lecture, we will be having the following as the contents: incompatibility of five-fold rotation and translation in two-dimensional space, Bravais lattices, coordination number, nearest neighbor distances, atomic packing factor for simple cubic, body centered cubic and face centered cubic structures. I will go back to the previous lecture with the intention of showing again the incompatibility of the five-fold rotation and the translation in two dimensions. Let us look at the picture. Let me ask you the question. I told you about the lattice point A, and we have got the vector A ending at this lattice point. Let me ask this question: supposing you rotate this vector along this direction, if the angle phi becomes 90, what would happen? This is A, remember this is A and this is again A, right. The distance between any two lattice points will be the same. This is also A. Supposing I rotate and end up with the lattice point, and if the angle through which I rotate is 90 degrees, what will be the unit cell? What will be the shape of the unit cell? Remember, this is the lattice point, this is another lattice point, this is rotated through 90 means it will come here, right. So, when the lattice point comes here, the whole thing, this thing will be what is the shape? This is a square shaped unit cell, right. If the angle phi is 90, by rotating through 90 degrees this vector, you end up with the lattice point, then you have a lattice point here, you should have another lattice point here, right. Then this will be a square shaped unit cell. So, if phi is 90, you will be getting a square shaped unit cell. If phi is 180, what will happen? You will be getting a rectangular unit cell, right. If phi is 90 pi by 2, then we will end up with a four-fold rotation. What is meant by four-fold rotation? If the fold length of rotation is 4, that means it should be a square lattice, because if the square is rotated through 360 degrees, it will occupy the same configuration 4 times, right. So, it is a square lattice. If n is 2, the fold length of rotation is 2, that means it is a rectangular lattice. Therefore, I would like to impress upon you the fact that phi is ruled out. That means, if you have a pentagon here, right. Now, a pentagon will not form a unit cell to fill up two-dimensional space. Remember again, a single pentagon will have definitely a five-fold rotation axis, but stacking pentagon side by side, you will be end up with the miserable situation, namely the filling up of two-dimensional space will become an impossible thing. By stacking squares, you can fill up two-dimensional space, by stacking rectangles the filling up of two dimensional space is possible, but not by pentagons. This is what I want to emphasize again. With this in view, I am showing this picture. Now, we will move on to, there are 5 possible two dimensional lattices, right. One of them will be A 1 equal to A 2, phi is not equal to 90, A 1 equal to A 2, and okay, there are things that are given here. You see a square lattice, okay. You have got a lattice here, a lattice here, and so on, right. So, these are the 5 possible lattices, the cell dimensions and the angle between the two vectors, right. This is a square lattice, A 1 equal to A 2, phi is 90 degrees, this is square lattice. The other things are shown here, okay. They are the 5 possible two dimensional lattices. It is Bravais who showed that there can be only a certain number of lattice types in 3 dimensions. What do you mean by 14? I mean a certain number of lattice types. I am making you to understand the wall in which we are sitting. It is made up of bricks. The brick has got a particular length, particular breadth and particular thickness, and that is the fundamental building block. Now, we ask the question, in the whole universe, you go to Neptune or Pluto or any other planet or any other thing, it is the mathematics, the mathematical theorems say, it is not physics, the mathematical theorems show that there can be only 14 types of arrangements of lattice points, right. You know what is meant by lattice? It is an array of points in space, an ordered arrangement of points in space. There can be only 14 distinct ways in which the points can be arranged in space, so that the entire space is filled up, right. So, there can be only 14 possible lattices. You know, the wall is made of a brick with a particular dimension. Instead of this dimension, you can ask the question, can you have a brick, a square shaped brick? The Buddhist monks in the prayer halls, they used square shaped brick. The brick length and breadth will be same, thickness, you can have tiles length and breadth having same values, breadth may be smaller, right. So, if you ask the floor, the construction of the floor or the bottom or the top, what should be the building block, nature of the building block? Building block may be length and breadth may be equal or may not be equal. So, similarly here we ask the question, what about your A, B, C, the length, breadth and height and the angles, right, angular relations that are being present or connected, A, B, C are connected by what are the angles by which they are connected. So, the angular relations for the 14 possible lattices or for 14 possible bricks. In a crude way, I can talk about 14 possible shapes of bricks, right. Okay. Out of which you talk of plutonium or iron or copper or selenium or a semiconductor like silicon or germanium, any kind of lattice or ionic solid like NaCl. We have studied considerable amount of things regarding bondings in solids. All solids irrespective of bonding, whether NaCl or MgCl2 or silicon or copper or iron or whatever be the thing existing in this planet or any other planet or anywhere in the universe, mathematics says that there can be only 14 possible shapes or fundamental building blocks, right, the shape of the blocks. Now, these things are proved, mathematically proved by Auguste Bravais belonging to France, and these lattice types are known as Bravais lattices, right, named after Auguste Bravais. So, in 1848 Bravais demonstrated that in a 3-dimensional system there are only 14 possible lattices. A Bravais lattice is an infinite array of discrete points with identical environment, but a lattice means it should have identical environment, and these 14 lattices come under 7 crystal systems. What I mean by crystal system is I will name cubic system. A cubic means it may be simple cubic or body centered cubic or face centered cubic. So, under cubic we will have 3 kinds of cubes: simple cubic, body centered cubic and face centered cubic. Now, therefore, there are 7 crystal systems. Out of from the 7 crystal systems will emerge 14 lattice types, right. Simple cubic, in the case of cubic, got one lattice system, one crystal system is cubic, but there will be 3 lattices: simple cubic, body centered cubic and face centered cubic. Lattices are characterized by translation symmetry. Let me repeat, lattices are characterized by translation symmetry. You go from one point to another point, there is nothing to distinguish between this point and this point, or some this point and this point. The lattice looks to be similar. That is what we mean by translational symmetry or translational invariance. Nothing to distinguish between this lattice point and some other lattice point here, or this lattice point that you have got here and this lattice point or this lattice point. They are indistinguishable, they are identical, they are similar, right. So, this forms the fundamental building block, right. This is a crystalline solid, not a amorphous solid. Amorphous is the one in which the atoms are arranged in a disorderly manner, right. Glass, mica, they are amorphous, whereas a crystalline solid is one in which there will be a fundamental building block, and this is repeated. It is something like brick. You have got a brick here, you have a brick here. This is the one that you have got here, right. Brick is repeated, and so on, right. So, this is the fundamental building block. It is repeated again here, they repeated here, and so on, right. So, this is the crystal and this is the fundamental building block, right. The crystalline solid is one which is rigid, having long range order. What do you mean by long range order? You have got a orderly arrangement of atoms. You have got atom here, atom here, atom here, atom here. It is infinitely periodic system, right. In principle, a single crystal is a ordered one. Throughout the entire volume, the atoms will be arranged in an orderly manner. It is called a single crystal. So, whether it contains atoms, molecules or ions, they occupy specific positions, and this is a unit cell. What is a unit cell? It is a fundamental building block or the smallest repeat unit of a crystalline solid. This is a crystalline solid, right. This is a repeat unit, this is a fundamental unit, right. Something like a wall. Wall is the bigger thing, and the wall is made up of bricks, right. And so, similarly, this is a single brick and this is a wall, right, out of which the wall is made up of bricks. By translating or placing one brick above the other, right, another brick and so on. Okay. So, at the lattice points you may have an atom or molecules or ions, right. I will again try to emphasize this particular point, I will come to that later. As I told you just now, there are 7 types of unit cells, right, 7 systems or 7 types named after Bravais, they are called the Bravais lattices. What are the 7 types? One is cubic. You have got in a cube, all of you know that the length of the sides are all equal, A equal to B equal to C. Angles alpha, beta, gamma, again they should be equal, and they should be equal to 90 degrees, right. This is cubic, right. The tetragonal is one in which A will be equal to B and not equal to C. It is a tetragonal, right. You see A equal to B, not equal to C. The angles are again 90 degrees, and if all the lattice parameters are differing, such as A not equal to B, not equal to C, right, it is orthorhombic structure. A orthorhombic structure is one in which the lengths of the sides are unequal, but the angles are equal, right. The alpha equal beta equal gamma equal to 90. Rhombohedral is one wherein A equal to B equal to C, angle alpha will be equal to beta, that will be equal to gamma, but gamma is not equal to 90 degrees. A monoclinic is one where the sides are unequal, alpha not equal, A equal not equal to B, not equal to C. The angle, the 2 angles alpha will be equal to gamma, that is equal to 90, but beta is not equal to 90. Triclinic is the one in which there is no symmetry, in the sense that the sides are unequal, the angles again are unequal. I mean alpha is not equal to A, not equal to B, not equal to C, alpha, beta, gamma, they are unequal, they are not equal to 90. Hexagonal is the last one that you come across here. We have been talking about Bravais lattices. Bravais is a famous person in the sense that in the whole of solid state physics, as I told you, the properties of materials, they depend upon the two factors, namely the structure of the solid or the structure of the unit cell and the bonding. What do you mean by structure? The positional arrangement of the atoms, right. That is what you mean by structure. You have got atom here, atom here, atom here and so on, right. The positional arrangement of atoms. So, the credit goes to Auguste Bravais, who showed that all solids in the universe should be crystallizing in one of the 14 lattice types named after Bravais. Is a mathematical proof, right. So, there is no question of asking whether the 14 is the right number, if and buts in the 18th century, but not now. Mathematically proved beyond doubt that there will be only 14 lattices, and the lattice types can be X-rayed. So, X-ray diffraction is a powerful tool using which the position of the atoms in different solids can be studied. And so you have the cubic structure again, and the 7 systems I am again reading: cubic, tetragonal, orthorhombic, hexagonal, monoclinic and triclinic. So, 1, 2, 3, 4, 5, 6, trigonal is the 7th one. You have got I is the body centered, F stands for face centered, C stands for side centered. There are 7 crystal classes and 14 Bravais lattices. Okay. You see here 1, 2, 3, 4, 5, 6, 7, and then there are the cubic lattices are there here, right. 1, 2, 3, 7 plus 3. Okay. In all there will be 14 lattices. You can count literally, there will be 14 lattice types, that can be only 14. Okay. Then I am showing these 14 lattices in greater detail here. Once again, one of them is triclinic, monoclinic. The reason why I am showing this again is cubic will have 3 kinds of lattice types, right. Monoclinic, one is P primitive and C is the side centered, that is the atom at the lattice point the center, that is called side centered, that is the reason why I am showing this again. And orthorhombic, you have primitive, side centered and body centered, you have a atom at the body center, right. So, this is face centered, you got atom at the face center. You got a tetragonal primitive means as I told you, in the primitive unit cell is the cell in which the atoms or the lattice points will be found only at the corners of the cell. You see here lattice points are found only at the corners, there is nothing inside the cell. Okay. That is the reason why it is called primitive, right, primitive. And I, as I told you, is body centered. Okay. Now, you see you have got a, in the tetragonal system you have got an atom at the body center. This is primitive, you do not have anything inside, you have got atoms at the corners, but you have got an atom at the center in addition to the atoms which are found at the corners. This is the tetragonal unit cell. Okay. Then let me not spend too much of time, the rhombohedral, the hexagonal. Then as I told you, I will come back to cubic. I will spend some time now on the cubic structures, because it is easier to deal with the cubic structure from the mathematical point of view, and again from the physical point of view there are many solids in the whole of periodic table. I will show that later. In the whole of periodic table you have got several elemental solids and very many solids crystallized in the face centered cubic structure. What are the 3 different cubic structures? As I told you earlier, it is P the primitive, it is you find atoms at the corners only, right. It is a simple cubic, it is called simple cubic. P refers to primitive, that means atoms or the lattice points will be found only at the corners. Okay. Then it is body centered. Okay, you have got atoms at the corners, and then there is one atom at the center of the body, center of the cube, right. It is called BCC, body centered cubic, at the center of the body, right. The body here, the center of the body. There are many solids. Iron, our mother earth contains lot of iron. We are all sitting in this room or anywhere, we are subjected to a magnetic field, where mother earth is a magnet. We are all living in a, we are sitting on a magnet. Earth is having magnetism, north pole, south pole. No. So, the magnetism is due to iron, right. At the interior of the earth, you have got lot of iron. The iron is body centered cubic solid, right. Iron, the structure of iron is body centered cubic, right. So, do not ask what is structure of iron at the earth interior, right. There are many problems, right. The earth interior, it does not have solid iron, the molten state, you know, when you go deep into the earth, it is still very hot. It is very hot when the early universe was started, but it is still hot. You know, molten iron is there. We are all sitting on the molten iron. Okay. So, iron in the laboratory, right, you have got a piece of iron, many places, all the girders and the rail tracks are made of iron. They are all having this crystal structure, body centered cubic structure, where we will have, if you carefully look at the fundamental building block, there will be atoms, iron atoms at the corners of the cube, and there will be one iron atom at the body center. Okay. Then there are number of solids crystallizing in the face centered cubic structure. This is a face centered cubic structure. What is a face centered cubic structure? In addition to atoms being found at the corners, there are 8 corners, right. You look at this face, at the center of this face there is an atom. You look at the top face, right, at the top face you have got an atom. Similarly, the bottom face is the center here, and similarly for this face you have got atom at the center for this face. For this face you have got an atom at the center, right. How many faces will be there? For any cube there should be 6 faces, right, 2 faces here, 2 faces here, one top and one bottom, right. At the 6 faces, at the centers of all the 6 faces, there will be atoms, in addition to the atoms found at the corners of the cube. This is called a face centered cubic structure, FCC. This is body centered cubic. This is called a primitive or simple cubic structure. This is simple cubic. So, in the cubic system, there are 3 different kinds of structures: simple cubic, body centered cubic, and face centered cubic. Among the 3, very many solids, there are a lot of solids which are crystallizing in the face centered cubic structure. I will come to the reason why very many solids crystallize in the face centered cubic structure, and almost you have to search for examples, right, for solids crystallizing in the simplest structure, namely simple cube. The nature is so very complex, right. Nature is so very complex, it does not allow us to deal with simple systems. There is alpha polonium is an example for simple cubic system. There are only 1 or 2 substances crystallizing in the simple cubic structures, but there are very many solids crystallizing in the face centered cubic structure. The reasons for it, I will come to that at a later stage. Now, let us look at the simple cubic structure. You all know now, by now, a simple cubic structure is one in which you have a cube, you have got atoms at the 8 corners, right. You have got the 8 corners. You see a cube here, right, inside, but anyway the point is you have got 4 at the top and 4 at the bottom, and the atoms are at the corners. Cubic unit cell is a 3D repeat unit. This is a 3D repeat unit, rare, only polonium as this structure, only polonium as the simple cubic structure, right. So, alpha polonium, right. Generally you have to search for example, I mean it is very rare, right, it is a rare kind of, I mean, you know, you have got alpha polonium is the only system that has got a simple cubic structure. And then we pass on to the coordination number. How do you define coordination number? It is the number of nearest neighbors. You take any atom at the origin, you got any atom, you know, it is a lattice, it is periodic. Any atom or any lattice point is equivalent to any other lattice point. You can choose any lattice point as the origin or any atom as the origin. Okay. The repetitive pattern, and therefore, you look at this atom. Okay. Now, how many atoms are there equidistant from this atom, or the number of nearest neighbors, one at the top, one at the bottom, one on the left, one on the right, one on this in this direction. So, this is x direction, this is y direction, is the z direction. The coordination number is 6, right. This atom is surrounded by 6 atoms, right. You can visualize or imagine a simple cubic structure, the coordination number will be 6. Okay. So, the coordination number is nothing but the number of nearest neighbors. How many atoms are found nearest to a particular atom, right. The nearest and second nearest, supposing you take an atom here, this is the nearest, right, this is the nearest, the dark ones are nearest, the white ones are slightly far off. You look at this atom, this is far away from this one, right, but whereas there are certain atoms are found to be very close to the atom, the closest atoms are said to be the nearest atoms. How many are there is the coordination number. So, coordination number refers to the number of nearest neighbors. Okay. For a simple cubic, the coordination number is 6. This is what I told you just now. For this atom, there will be 6 nearest neighbors, 2 plus 2, 4, 4 plus 2, 6 nearest neighbors. Okay. So, for simple cubic, the number of nearest neighbors is 6. This is important, right, in the sense that we have to calculate what is called the atomic packing factor. What is atomic packing factor? If you look at the whole volume of the unit cell, to what extent the atoms are filling up the whole of the unit cell, that is called the packing density, right. You have a vessel, if you have water, the whole volume of the vessel can be filled up with water, but here you are given some space, but the atoms are spherical in shape. So, the spherical atoms will not be able to fill up the entire cube, right. So, there will be left out space. So, the extent of filling, the space filling is called the packing density, right. You fill a box with hard spheres, you take a box or you take a cubic structure, fill the box with hard spheres, right. You assume the atom to be like a sphere, right, and then make the atoms to touch with each other, right. Whether atoms can touch each other in a solid, let me ask you a question, a fundamental question, whether the atoms can be touching each other. What is an atom? Atom is made up of nucleus and the electrons, right. If the atoms are touching each other, the electrons will be touching each other. Whether the what about electron? It is a negatively charged particle. How can one electron touch another electron? They are negatively charged, they should be repelling each other. Therefore, the atoms touching each other is an approximation. The hard sphere model, again I will repeat, the hard sphere model which is used for calculating the packing density or packing fraction or packing factor is an approximation. To determine the extent of space being filled up by the atom, you are making use of a hot sphere model, this is only an approximation. Packing factor is nothing but the ratio between the total volume of atoms or spheres in a box by volume of the box. As I told you, if you have a cubical wall structure, you have a cube, the atoms being spherical in nature, the entire volume cannot be filled up by spheres, right. When you are having spheres, there should be some left out volume. So, or the maximum extent to which the volume of the box is filled is given by the APF, the atomic packing factor. The question is, what is the maximum packing factor you can expect in simple cubic, then body centered cubic, then face centered cubic. Then you pass on to other structures, all the 14 lattices, the question can be extended. In crystalline materials, atomic packing factor is the total volume of atoms in unit cell by volume of the unit cell. So, the APF is defined as the volume occupied by the atoms to the volume of the cell, right. This is so called atomic packing factor. Let me now summarize today's lecture. Out of the 14 Bravais lattices which we have been discussing, there are 3 coming under cubic system. They are simple cubic, body centered cubic and face centered cubic. You should remember most of the solids crystallize in the FCC structure. Let us pass on to the question session. The questions are: what is meant by coordination number? What is the meaning of the words nearest neighbor distance? Give an example for a simple cubic structure. With this we come to the end of this lecture. The rest of the things we will see in the lectures to come. Thank you.